Hello everyone. Today I'm going to deliver a lecture. The lecture topic is inelastic seismic response and effect of material nonlinearity, or we can say inelastic seismic response. This is the main focus on the topics. So let's start. So in this topic, it will be contained. We will first discuss on effect of the material nonlinearity, then elastoplastic force deformation, and then inelastic response, inelastic structural response, and then inelastic behavior and ductility, and the force reduction factor and ductility, and then response modification factor are for the structural system, and ductility of the confinement. So let's start from the beginning. Inelastic response of inelastic seismic response or effect of the material nonlinearity. So here is our topic. We can see uh, inelastic. At first, the we can see the effect of the material nonlinearity on the plastic condition. When plastic conditions, the material natural frequency is decreased, then vibration will be slow. So we can see the linear. It will be gone as a as it will be gone until the it will be gone continuously. So the linear, we know the linear equation: P equal to Ku, P equal to force, K equal to stiffness, U equal to displacement. So you can see another inelastic response, so equal to ultimate and ultimate. So we can say when is plastic, then the stiffness is 0. When the displacement is reduced, we can say displacement is reduced, then K is also reduced. When the displacement is increased, so you can say displacement increase, then also stiffness also increase. So we can see here another another graph. We can see here the when the natural frequency, we know the omega equal to root over k by m, which is 5 radian per second, and time period 1.25 second. So you can see that one cycle is completed 1.25 seconds. So you can see in vertical direction is displacement, and x direction is time. So we have found 1.25 is for one cycle. So if you drawing here, so you can see here 1.25 is completed one cycle, and then another is one cycle, and another is another. So it will be going on ultimately. So we can see here for how many cycle is completed. If we calculate it, then we can see 1 2 3 4 and 4.5. So we can see 4.5 is cycle is completed within the 5 second. uh, so we can conclude that the 6 seconds, so it will be 6 seconds. Within 6 seconds, the only 4.5 cycle has the fully one 4.5 second is completed. Okay, so let's see compare the different lines. So at first we've been seeing the line is fully line. So we can see here the fully line is gone this way, and ultimately gone this way. And we have been seeing the 5 second. The line is completed 5 second only, four cycle. The cycle is completed 4 cycle. On the other hand, we will see the dotted line, it is also completed, but it is take 3.5 cycle. So it will be more or less. We can see another cycle is given is what I will say, the circular shape, and it is take 3.4. It is completed 3.4 cycle within the 5 second. And last one, we can see the this is the what I will say, it is the red color of the cycle. You can see 2 cycle has completed fully, 2 cycle. You can see here 4 cycle it consists within 5 second. So this red color is not what I will say, this is not for good. As the steepness is decreased, then it will be slow, and deflection will be increases. Okay. So you can see here, here we have extracted here from another a professor, prominent professor, Dr. Iftikar sir, University of Asia Pacific. So you can see here he is giving some example which what is the effect of material non-linearity. So in the figure we can show 3.1. This is the 3.1, and representative then undamp which is C is equal to n k m equal to 1 kip per feet square, and system is non-linearity, and elastic and stiffness is given 25 when u equal to greater than uy and equal to 0. So another figure we can see 3.2 is shown the dynamic response of the step loading which p equal to 25. So it is also step loading is given here, and in this case we can see here the according to the increase of the nonlinearity, the first result of the linear system, while the other three of the nonlinearity system is yielding displacement is given y equal to 1.8, 1.5 and 2 respectively. Here is the linear system, and displacement we taken y uy equal to 1.5. So these are the material nonlinearity, and if we see the system when elastic is very difficult for earthquake, and inelastic is ductility also very good for the ductility is very good for the earthquake region. So you can see in the deflection is x-axis, in y-axis is the force or stress is given, and in this region we have been seeing the plastic region. So if the area of the plastic region, you can see the energy absorption. If the material is taken the more energy, if the material is absorb energy more, then it will be good for earthquake design or earthquake resistance design. Or we can see that if the materials or structure take the more deformation, more ductile, then the structure will be good for earthquake resistance design. So here is another formula, the yield reduction factor or force reduction factor, which is F naught divided by F yield, and another is ductility factor, which is UM divided by U ultimate. So so another picture we have been seeing the ramp load and step and elastoplastic root. So ramp is initially is increase linearly, is increase linearly slowly. On the other hand, we can see the step loading. It is directly, it suddenly increase, and this goes the and this goes the plastically. And the elastoplastic is the same. It is same, almost same as is the ramp stop loading. Uh, we can see another is for or yield displacement factor. Okay, so we have been completed here the elastic and effect of the material nonlinearity and elastomeric plastic deformation. So we can now we have been seen some assumption of material nonlinearity. The main observation of this result, the displacement increase are more linear system because the reduce of the equivalent stiffness, and the maximum displacement for system 2.2, 2.5 and 6.5 and nonlinearity is prominent in this second and third case, as it only be started 1.8 and 1.5 feet respectively. Okay, so you can see our out of maximum displacement of around 2 feet, so you can see here 2 feet, um, but it is promoted of the fourth cases. Okay, we've been seeing the fourth cases, and however it is representative the maximum force of spring in this case are 50, 45, 37.5 and 30 kips. It is shown that this despite the magnified displacement of this force reducing the material nonlinearity. And then third is natural period of the meaning of the nonlinearity system. However, the dynamic response is still indicate the periodically, which is interpret in terms of natural frequency or period. The natural period of the linear system is 1.257 second, which is increase 1.3, 1.25 and 1.3 seconds. This nonlinear system due to the decrease of stiffness of system. And last one, we can see the since of the material nonlinearity elastic and not inelastic does not fail and completely integrating and nonlinearity or residual displacement structural fail cannot be shown. So these are the explaining here the main observation of this here. So now we can see here elastometric pairing, elastometric force deformation. So now we'll go to here the elastometric force deformation. So this graph is representing the elastometric system of the corresponding linear system. It is shown the non-linear system. Here is the force is remain proportional to the deformation. This is the force and proportional to the deformation, and beyond which is force remain constant up to the failure, which is these are called the elastometric force response. Okay. On the other hand, if the system is remain linearly elastic, this if you consider here, and the corresponding force and deformation will be F naught. So this will be F naught, and the U naught. This is the U naught, which is the displacement. And when F naught greater than Fu, this is F naught greater than Fu, but E naught, which is the E naught, less than the that's less than the This is the elastometric force deformation, we can say. Now this again emphasizes that although the nonlinear system has to be withstand a similar force up to the yield strength only, the deformation this is the last one, it must be withstand before the failure greater than. Both case aspect needs to be incorporated to the structural analysis and design member subjected to the seismic vibration. Okay. So we have been seen here. So we have concluded here, and another we can see elastic response, inelastic structural response, or okay. The ratio between force and F naught and Fy is called yield reduction factor. So we are going here yield reduction factor. Okay. Or force reduction factor, we can say, which is denoted by Ry, where is denoted Ry, and while the ratio between deformation and Ut, this is from this graph, and Ut is ductility factor. We are already shown here. The yield reduction factor, Ry equal to F naught equal to Fy, and ductility factor equal to divided by Uy. Okay. Using Ry equal to F naught in this equation and found equal to U. So we have been seen here the inelastic response spectrum. Okay. Ry equal to 1. We can see another example is given here. So I am going here for yield or reduction factor. These are the graph we have been shown here. For inelastic response, Ry equal to 1. For Tn greater than less than Tn, where root over mu minus 1 and mu for Tn minus T. The intermediate value between T and B for between C1 into C can be denoted by interpolation, and here CA is given, TA is given 0.03 and TB is 0.125, while TC1 and T depends on the damping ratio of the system. For the damping ratio 5%, the reasonable the assume TC1 equal to 0.35 and TC equal to 0.55. Okay. So we have been seen here U ultimate equal to 1.2 and U not equal to 0.2. Let K equal to 25. So if you know as from the static for equation f equal to k u mean delta f equal to is not given, so k is 25 and u equal to given is 1.2, so fy will be 30 ksi. It is for yield or plastic. For elastic, f equal to k equal to f naught, so all value will be naught, so k is remain same, but u equal to it will be used for elastic, and it will be found 50, so 50 is greater than the yielding. Yielding we have found 30. On the other hand, we have been found elastic or plastic if it is 50. So we can see that if we design in previously 30, then we can design for 50 as the ductility has increased. Okay, so let's see yielding reduction factor Ry f not equal to fy, which is we have been found 50 divided by 30, which is 1.65. Okay. Tn we have been found 0.4, so if we go to the if we go to this diagram, t equal to 1.4, so 0.4, and the graph is 8, u equal to 8, and if we know the Tn equal to 0.4 and ductility factor is 8, then what will be R? We go to the 8 and ductility factor will be from this graph we will be found this here it will be almost 5. Okay, almost 5. So this graph we have been seen here, TA, TB, TC, and 0.6 is here, and time period is x-axis and y-axis and the yield reduction factor. Okay, so Ry equal to 1 when Tn and T equal to greater than 4, all the parameters given. Okay, so let's see another response modification factor. Okay, so I have been calculating inelastic base shear. Maybe how can I? Okay, I'll see another example for here. Okay, this is the calculate the inelastic base shear B. I will say another after this. Okay, calculate the elastic base shear for inelastic, sorry, it will be inelastic, that means plastic base shear B for the corresponding relative displacement U max for L centro data are given in a single degree of freedom. So all data are given. We have been damping ratio is 0.005, Tn equal to 1.275, Un equal to 0.375, and base shear is 9.4, and Uy equal to 0.15, and W equal to 0.10 pound, and K equal to 100, and Ub equal to 0.2. So what will be we have to calculate the inelastic base shear. So let's see here. We have been see Ry equal to U naught divided by U ultimate, which is 3.7. So if we get the ratio of the what I will say Ry, which is called Ry, which yield reduction factor. If we get the yield reduction factor, then we have found 3.75. As per this graph 3.75, we have been found T equal to 1.275. So intersecting this point. Okay. Another we can see here mu equal to 0.375 we have been found from Tn versus Y graph. Tn is given, we have been seen 1.275, and in this way Ry is we have been taken from this graph. How we'll get this? 3.76. So 3 is here, 3.76 is here. So we are getting intersect in this point. And in this way, we've been found to mu value 3.76 from the graph Tn versus Ry graph, or mu equal to sigma 50c divided by sigma naught graph. Okay, so base shear will be base shear bc divided by Ry and found 2.5 kip, and um equal be mu equal to uy and divided will be 3.75, which 0.375 feet. Okay, so these are the first we have been we are solving, and the second one we can see the data parameter is given remain same for L2 data, so we can calculating for second one. So let's see here. Second one, we know the parameter weight is given and mass given stiffness, and we can find out the natural frequency and the time period 0.1. So when we get the time period 1, then we are taking the LCM to ground motion, so we can found the structural response, which is C 2.325 from LCM to Tn versus C graph. And Z we have been given 0.313 as we have been seen the it is given. Now elastic base shear, we know elastic base shear equal to Z CW, and putting all these value and found 7.626, and K equal to U naught equal to KB, and putting all these value and found the U naught equal to 0.026 inch square. This is here. This is not the ultimate. This is not the proportional. It is the U naught, and found after an F naught also found 7.26. Here is F naught. We can see base shear, but it will be a F naught. And Uy equal to 0.2 is given in question. We have been seen here is given in question. So if you know the Uy and U, we have been calculated also U naught 0.076. Then corresponding we have to calculating Ry. Ry we know U naught divided by Uy, ultimate. Y means ultimate at pound 3.36. So inelastic base shear, you can see ZIC by W, R value is given 3.6, and divided 3.6 and found 2.2 pound. Okay, so let's see. We have been found the time value 0.01 as we have been calculating here 0.01, and putting this value in graph 3.01 with respect to we have been found Ry 3.36. Okay, so all are the same. If we calculate the from time period time period versus Ry, you can found the R value. On the other hand, if we calculate U naught divided by Uy, then we will also found 3.663. So we have been seen U equal to 10.13 from Tn versus Ry graph, and Um equal to mu equal to Uy, which is 0.236. Okay, this will be another results. And first result we have been found the displacement here 0.376, and we have been found 0.203. So these are the less than the previous results. So now we can see the response reduction factor. So you can see the response modification factor R for the structural system being BC 2020. The moment resting frame, no shear wall. For the special moment resting frame SMRF, which is value of R will be 8, and intermediate moment resting frame R will be 5, and the ordinary resting moment it will be 3. So we are calculating here how we'll get the value of Ry 3.36, or we have been seeing how to calculate R value. We have been found 3.63 or 3.36 here. So now we've been seeing here inelastic behavior. What I will say, this is also completed. So these two also at first I have completed. So now I am seeing here inelastic behavior ductility, inelastic structural response, and inelastic behavior or ductility. So I'm also completed here modification coefficient of R is which is found, uh, it is taken from the code. uh, so if we want to see here, we can see here the broadly is given the modification response coefficient R value is are given for the bearing wall system. We can see the special RC wall ordinary shell there. In this case we can see no frame, that means it will be bricks wall. So it is the very complicated in our country. The most of the building are it is abandoned, the no frame wall is not used, as a bricks wall is prohibited, avoiding as the seismic effect it will be very high. That's why we are not using this case. But on the other hand, we've been seeing another building frame system with shear wall and bracing. If they use shear wall bracing, then and the special RC wall will be 6 and ordinary for 6. And ordinary bricks masonry wall, it will be this value. In this case, moment resisting frame, it will be using as usually. That means moment resisting frame means beam and column system. It is called moment resisting frame. So if we use special in moment resting frame, it will be SMRF it will call, and it is 8. And the intermediate if you use, then we can use concrete for 5 and steel for 4. And ordinary if you use, it will be 3.5 or 3. So on the dual system means it will be shear wall plus beam plus column wall. It is the dual. These are the dual system. A special RC wall we can see 7, and ordinary RC wall we've been use 6, and the others parameter is given. But most of the cases we have been used for 6 up to 6 stories we can use moment resting system, which is beam column system. And if we use the ordinary, then it will be 3.5. And we have been seeing the in our calculation we have been seeing the R value we have been found at 3.36, and another calculation we have been found R equal to 3.776 and 3.63. It is, we can say the value is very close to this value. Or if we use the intermediate moment resting from the concrete, it will be a value of R will be 5. So there is no issues. Okay, we have been completed this lecture. So there is another how we'll get the value of ductility or inelastic behavior. So let's see. Here is the inelastic behavior of ductility. You can see in this graph very clearly. So axis is the displacement, y is force or shear or base shear. You can see the value of R U equal to found Ry divided by E. On the other hand, if we how will get the R value, the value will be Ry, which is B divided by D, or Ru divided by multiplication factor of mu, which is given is here Be divided by By. B means base shear elastic divided by base shear ultimate. Okay. So this is the actual length we have been found from graph, which is design, which is ultimate divided by design, and design strength we have been found from here. And we have been the dotted line. The dotted line is inelastic bilinear envelope, we can say. And inelastic we have been found mu d, which is B yielding divided by D. We have been also here inelastic behavior or ductility. There are lots of theories given here. I am skipping this. and elastic behavior you can see R, how we'll get R B BE divided by D. So if we want to see the graph, we can see the axis is the displacement y axis into base shear. So these are going to elastic, and this is the inelastic. After the reaching the elastic load, that is in going to the inelastic continuously equation of the displacement we can see here. So we can, if we shaded at this region, then we can say that this is the equal area of the this region, and this region, this will be the same equal area. So these are the already discussed the long period of the structure. You can see as we have been seen the mu equal to yield ultimate shear divided by yield shear. So we can here the parameter of mu, the distance between B divided by B elastic, it is called R, or reduction response modification coefficient, and these are the given in graph, and where we can denote it by B divided by N, and this graph also design earthquake ground motion, and these are the pushover curve we have been seen here, and mu naught is the overstand factor, which is mu max divided by B. B means is the design earthquake, and CT is the deflection amplitude factor. Okay, so overstand factor we can use this, and CD is a deflection factor if we found the deflection divided by deflection yield, and using the reduction factor, then and we can found the C, which is the deflection amplification factor, and these are the same graph is given here. If we go to the inelastic behavior on building, this is the elastic limit, this is the IO, which is immediate occupancy, which is LS, which is the life safety, and CP, this is the collapse prevention. So all three parameters are given here. So here we can see clearly the immediate occupancy, this is the immediate occupancy, and life safety we have been here, this is the life safety, and the collapse prevention we can see here, this is the collapse prevention, and in this zone we can see the collapse. Okay, so let's it is completed. Okay, and this is also completed, and this is elastic behavior of ductility, it is also completed. Now we can see the ductility and confinement area. Okay, so go to here, so ductility and confinement area. So ductility of confinement, ductility means how many strain is given here. When we call the ductility confinement concrete, then we have to show the Kent-Park model. This is the Kent-Park model. Kent-Park model is given here. When we warping a cylinder with some rope, then the ductility will be more and more, because it will be not brittle, it will be not it will takes the more deflection. Okay, so buckling load, so we've been seen here the Kent-Park model is given here, which is strain 0.002 and strain 50 ultimate and 50 ultimate confined. Okay, and this is the strain we've been given, and 0.20 F prime C is given in this line, dotted line, and 0.50 is given is dotted line, and the ultimate F prime C is given. Okay, so this line is given when the concrete is unconfined. When concrete is confined, then we can say this result will be like this one. Okay, so we know the ultimate 60 equal to ultimate 50 divided by plus ultimate horizontal. I will get the ultimate 50, ultimate strain 50, strain 50 equal to 3 plus 2 f prime c f naught minus 1 into 10 to the power minus 3. I will get the strain 50 into horizontal. It will be found 0.75 root over PST equal to root over B into ST. What is the PST? Rho ST. Rho ST is the stirrup steel ratio, is the volume of the stirrup ratio divided by stirrup of the concrete, and B is a tie out of the tie, and ST is the spacing. And EU means the concrete confinement strain of the concrete, and F strain 50 U means concrete unconfined the strain, and F U50 is a hope or tie, and B is a tie outer dia, and B naught is the concrete to concrete dia. Okay, so let's see here. We can see the ductility and confinement is the several model have been suggested into the model, and nonlinear stress strain we've been seen of the Colgate. Among them, Ken Park model, which is 1971, is used to because the application of the confinement concrete is approximate stress strain relationship by a parabola of the ultimate strain is given, and beyond up to crushing of the concrete. So we can see that two equation is given here, and Z we have been found from this equation, and strain 50 is corresponding concrete strain. Okay, so we know the strain is 0 is which is 0.003, and ultimate we have been also discussing here in this one, so I am skipping here. This is the Ken Park model. It is it is using all over the world for confining concrete or for ductility purposes. Okay, so let's see an example. The calculate the strain confined concrete, which is strain U is given, which is unconfined for 6 inches stirrup spacing, and F prime C is 3 ks. The size of column and steel rearrangement is given below. That means here. So B is given, which is 12, and B also the D and B is also 12, and B is 9, and 1.5 is given from outer dia to this from this middle of the point, and B is given 8.6 inches square. And we can see here that 10 millimeter tie is used here, and the main die is 20 millimeter longitudinal one. So let's see which DST we have been found 10, and it is converted into inches, and AST will be pi by 4 into D square, and found 1.22 inches square, and B is found 12 inches, and A is also 12 inches. Both are the same. And BC is minus clear cover B plus minus clear cover, which is BC and AC are same, which is 9 cc, and B double prime is minus dia of tie divided by 2 here, and minus BC we can see BC and minus dia of 2 prime. This is also called AC, which is found 8.61, this is the 8.61. Okay, I'm erasing some below. So DST we've been found 10, and AST found, and in this way D bar we have been used 20 million B, and B we have been found 12, and A is 12, clear cover 1.5, and BI we have been found 9 c square. A is equal to same, it will be 9 also, and B double prime we have been found 8.6, and A double prime also remains same. For 6 inches square center by center spacing we are using the 6 inches center by center, and strain 15 ultimate or confined, you can say you confined or unconfined, we've been found 4.5 in 10 to the minus 3, and rho we have been using from this formula to 2 into B double prime plus A double prime into AST, and BCAC plus AST. BCAC core concrete of area, and AC AST, which is the stirrup spacing of the stirrup. Okay, we can see in this picture is given clearly, and putting all this value, and we've been seeing 6, which is the spacing is we are using the 6 inch square, that's why we is using 6. If we using another one, then we can found here. Okay, so if we multiply all this, then we will be found 486, and the row will be 0.0086. And now we'll calculating hops, which is 50 strain hops, strain 50 hops, 0.75 rho st root over BCST, and found 0.0079. And then last one we can see strain 50 confined. It will be used unconfined plus hope, and it will found 12.5 into 10 to the power 3. So it is found 3 times of 50. It will be almost 3 times of 50. If we see here 4.5 into 10 to the power 9, then we have been found here 12 into 4 into 10 to the power 9. So it is almost 3 times. So we've been seeing here the graph is shown in strain not equal to 0.006, and strain 50 is 0.0045. This, and another value strain 50 into confined is 0.1025 is given this portion, and this is the intersect on the 0.5% of apparent. If 0.25 the 0.25 apparent, then what will be what can we do? So you can use this formula in 148, and f is found 11, and we can see the similarly we can stirrup spacing. If we the stirrup spacing infinity 5 3, then what will be our answer? We have done this answer. We can see all the parameter we have been found. When the stirrup spacing 6, then we have been found volume 4.19, and B volume inch square we have been 486, and rho st found 0.0086, and appearance is same, and ultimate FU 50 unconfined found 4.5, and FU is 7.6, and F 50 into C into 10 to the minus C, which is found 12.4. This is the almost three times of this result, and Z value 48, and C if we use 2% of a prime C, then we can use 48 and 18.5, but it is not needed. But we have been seeing if we reduce the spacing, then we have been found the 4.5, which is strain FU ultimate unconfined, and for FUC confined we have been found 26, which is 5 or 6 times, which is 6 times of the unconfined. If we use the spacing is greater, which is 12 we've been used, then we've been found the ultimate unconfined strain is 4.5, and the confined strain it will be 7.3. It will be maybe 2 times. So you can see when the increase in when we can increase the what I will say, if we decrease the stirrup spacing, then we have been found the more and more confined strain. Okay, so you can use this. I am calculating this formula and using this sheet. Among these confined concrete model of Mendel, Bristol, and Kemp-Park, 1988 also widely used. Okay. So we can see another. They calculate the inelastic base shear for pile by die is given, assuming the ductility ratio of mu equal to 50, strain 50 divided by naught, and using Kent-Park model equation for confined concrete with clear cover 2 inches square and four number of 4 by ties stirrup is 10 inches square, and the given the base shear is 58 kip and ultimate displacement 0.07 inches square, and uy is given 0.02, and the mu is given 0.05, and time period 5.76 and u naught 0.002. This is the memorizing value. Also calculate second one, we have to calculate the corresponding inelastic displacement, which is u max. So let's start. We know the ry equal to naught divided by ultimate, which is 3.5. Then we can use the inelastic response or response modification factor, we can say. And b equal to b naught, or it will be found base shear for 2/3 ZIC from, and divided by ry, seismic modification response modification factor ry, and found 16.53 kip. This is the inelastic base shear, we can say. Number two, we can also calculate the corresponding displacement, relative inelastic displacement. We can and then we can use strain 50 unconfined using this formula, and found 4.5 10 to the minus 3. These are the all given data. So from this given data, we can see the DC, which is 20, D double prime, which is 59 9.5, and AST have been given pi by 4 square divided by 8, and found 0.196. And will be use the for circular section, we have been use rho pi d into AST from this equation, found 0.03. And hope elastic strain is hope, we have been used this formula and found 0.002. And now we'll adding two value for getting the strain 50 confinement, and found 0.006. Now if we calculate the ductility ratio and 50 divided by E, and if we now we'll get how we'll get this, we can use this formula, or we can use time period versus ROI graph for finding this displacement ductility factor, which is from 3.86. For inelastic behavior of displacement, we have been use this ductility with ultimate yielding displacement, and found 0.077. And we can see here when the column is tight column, then the displacement is much low. If we use the spiral column for ductility, we can see the ductility has been increased. So in this case, we are using in column when we design or constructing column, then we are using column as a spiral column for getting the more ductility. Okay, so the spiral column, the ductility is much more, we have been seeing this. That's why the phi ratio is 0.750 for spiral column is given is more, and 0.65 is less, because the tight column is ductility ratio is very less. We can see the shear failure. The shear failure always it is 745 degree along the from the axis. Okay, the lecture is in that. If you have any question, then let me know. Thank you everyone for your patience. Thank you.